Hello, I'm Joe Bakos, and I'm here today. I'd like to show you, demonstrate for you with a graphing calculator online, how to use the graphing calculator to demonstrate the use of quaterns, which is a new type of angle measurement that I've developed. And this new type of angle measure is able to translate between polar and rectangular coordinates using algebraic expressions. In other words, there's no transcendental functions, there's no imaginary numbers, there's no infinite sums. There are none of those things, and it is able to approximate conversions between polar and rectangular coordinates. A very good and simple approximation without using any of those things. And so I'd like to show you how it works. Now, in the links for this video, I will be putting links to the paper that I've written about it, and also links to this Desmos graphing site where you can, and so with these links you'll be able to both read the paper and also demonstrate the use of quaterns with a graphing calculator. So let me take a look at this. The first thing, one can find links to my papers here, and I will be updating these. These are not in the final form yet, but you will be able to find these papers once I upload them. In the next couple of days they'll be uploaded and current. And you can find it by going to the Vixra preprint site. So if you type in VIXRA into a search and you go to that site, and then in the search at Vixra, if you search my name, it is spelt Bakhos, and you search there, then you can find several different papers that I've written. Now, the one that we're looking for right now is rotation without imaginary numbers, and if you click on that, it will take you to my paper. But as I said, this is not the current version, and this will be updated soon so that you will get the current version. But once it's updated, it will be at the Vixra site. And as I said, I will, in the next few days, be putting links to the updated papers and also links to the Desmos graphing calculator that I'm about to show you. I am going to put links to all of this in the comments to this video. So the Desmos site that I will link to, as I said, is here. And so the first thing I would like to show you is just rotation in quaterns. And so this is the idea. So what quaterns are is a measure of the Manhattan distance, which is explained in the paper, what that means exactly. But the point is, you can get the angle measure in quaterns at this site. I mean, this is the formula for it, where Z represents the angle measure in quaterns. And this is how Z is calculated. But if you pick any X and Y coordinates here at this site, so let's suppose I just randomly pick X is 23, and Y is -8, let's say, okay? Then it gives the quatern measure. Since 8 quaterns is all around the unit circle, so 7.6 quaterns would put it in quadrant 4. Okay, and so then this is the angle measure in quaterns. This is the angle measure in quaterns. Now, as we scroll down here, This gives, to convert from quaterns into degrees, you just multiply by 45. And this is an approximation. This is an approximation. Okay? So it'd be 342 degrees. And then as you go down a little further, then this would be the measure in radians. It would be negative. So it would be, oh, actually, this is the measure in degrees, but negative. Okay. So that would be positive degrees. This is negative. And this is because, like the arctangent function in traditional angle measure, and this is another difference between measuring in regular degrees or radians and measuring in quaterns. In quaterns, the angle it just always returns you the positive angle, right? 340 degrees. Whereas if you use these arctangent functions and so forth in traditional technology, it will give you rotating, so a negative 19 degrees would be rotating clockwise. And so the positive angle measure in quaterns and radians would be this. So to convert from quaterns to radians, you multiply by pi over 4. And this is an approximation. It's not exact. And then this would be the exact value using the arctangent function. And I'm going to change this and put it in quadrant 1 so that we're looking at a strict comparison of positive to positive measure rather than comparing positive measure to negative measure. So let's just put it in quadrant 1. So let's change this. So as I said, in quaterns, the answer always comes up in positive angle measure, so counterclockwise, and that can be confusing. So let's just put it in quadrant 1. So here's the point, 23,8. And it's in quadrant 1. So quaterns, it would be 0.38 quaterns. As we scroll down, it automatically gives us the distance to the origin here. So in degrees, it would be 17.28 degrees. That is approximate. The exact value in degrees would be 19.17, 19.18. So you can see it's a little bit off. It's a little bit off, but it is a good approximation. And then in radians, the quatern approximation would be 0.3. And in radians, the true measure is 0.33. So we can see from this that quaterns deliver a very good approximation, to what the actual angle is. Now we can sort of go in the opposite direction here. Like let's suppose we want to input polar coordinates, right? Where let's suppose we input polar coordinates, and here I've got distance from the origin is 5, so that's the r value, and the angle measure in quaterns is 2.4. Okay, now these are exact values. As long as you stay in quaterns, it's an exact value. It only becomes approximate if you try involving theta. Right? If you try measuring in degrees or radians, then all this work in quaterns does become approximate, but it's a very good approximation. Now, as long as you stay in quaterns, this is exact. Okay, and so this, if you have a distance from the origin of 5 and you have 2.4 quaterns, the x-coordinate is negative here, 1.7. And the y-coordinate is positive, so that means we're somewhere in quadrant 2 somewhere. Okay. And so this site demonstrates that. Now, another site that I'm going to link to is to prove that quaterns can give exact values. And so I want to show you this kappa pi approximation. So what this approximation demonstrates is if n is the number of line segments that we are going to draw around the unit circle in order to approximate pi. Now, these calculations are all explained in my paper, which, as I said, I'm going to link to. So if this is a little too confusing right now, don't worry about it. But this is the major point here. The major point here is that nowhere on this page, in any of these calculations, is traditional angle measure referenced at all. It's not even referenced. The number pi is not used except for comparison. I put the true value of pi here, but this is not used in any of the calculations at all. Okay, and so no degrees are used, no radians are used, no reference to any traditional angle measure are used. The number pi is not used in the calculations, and yet using quaterns, you can get an approximation to pi depending on how many line segments you want to generate. So here, the only thing you want to change on this page is the number of line segments for the approximation. And as I add add line segments, the approximation becomes better and better, and it can be done to any degree of accuracy you would like. And what this proves is that quatern measure is completely accurate. It is completely accurate as long as you stay in quaterns and x and y coordinates. And so there is a very real basis for the reason that using quatern approximations can approximate well all of the trig functions and the inverse trig functions. So once again, I'm Joe Bakos. Thank you for joining me today, and I will put those links in the comments to this video as I said. Thank you very much.